3.7 will be our last section of Chapter 3. And this section is about optimization. So optimization is really what its name says. It means trying to find an optimal value for something. Sometimes that optimal value means to make something as big as possible. Sometimes that optimal value means to make something as small as possible. Right? You want to make the bill at the grocery store as small as possible and get the most amount of food for your money, that kind of thing, right? Optimal values. So some guidelines from optimization, and these don't always fit for every problem. They're guidelines. Often it's helpful to make a visual, sketch, a table, something that you can see. Doesn't always happen, but often it's helpful. To identify quantities that are known and those to be found. That's pretty much an always thing. You're given something, you need to find something else. Write any applicable equations and identify what quantity is to be optimized. Right, so the one example sort of verbally that I just gave, my optimization was to minimize the bill at the register of the cashier, right? That's what I'm trying to minimize is my cost. And then to write that equation in terms of only one variable. So sometimes there's a little bit of algebra involved in doing that. So like if you're dealing with something, we're going to deal with the first problem. It's going to have some area involved. And length and width are two different quantities. But we have to find a relationship between length and width in order to minimize the fact that there's, or to eliminate the fact that there's more than one variable involved, okay? And then step 4 is the actual calculus step. So not until we get to step 4 are we doing any calculus. We're determining the maximum and minimum values that are allowed. I'm sorry, step 5 is the calculus. Step 4 is before that. To determine maximum and minimum allowable values, if any, of the variable you're using. So sometimes you have limitations, right? So when I'm going to the grocery store, there are some limitations of what I have. I only have so much money in my wallet. So I do have a limitation in what I can spend. There's only so much food in the store. There's a limitation in what I can buy too. So, and then step 5 is to actually use calculus to find the extrema. And if you want to write a note to yourself in the part where it says use calculus, we're talking about derivatives, right? I mean, in order to find a maximum minimum value, this whole chapter has been about finding derivatives. So on step 5, we'll be finding derivatives, setting them equal to 0, either looking at sign charts or using a second derivative test, something like that. All right, the first example that we're going to do is a type of problem that you've seen done before, but with other techniques, in particular algebra techniques, and I want to show you how it can be done with calculus, and then we'll extend our ideas to other examples that maybe you haven't seen used quite as frequently. So a 3-sided fence is to be built next to a straight section of river, which forms the 4th side of a rectangular region. The enclosed area is to equal 1,800 feet squared, or square feet. Find the minimum perimeter and the dimensions of the corresponding enclosure. So as soon as I started reading the description, or you started reading the description, immediately you have an image in your head of this particular picture, right? You do, because there's just such good visual descriptions that are given. So the first thing we're going to actually do is we're going to draw the image of what they've described. So it says that we have a river, and we're going to make a rectangular enclosure along the river, and one of the sides of that rectangular enclosure is actually going to be the river itself. So we're going to have something like this going on. Does that make sense for everybody? And it says straight section of the river. I just made mine look wavy to remind you that it's river, that's all. Okay. So some things about this shape. It is a rectangle, right? So you know what the area formula for a rectangle is. It's something that you've known since elementary school at the very least. So what is the area of a rectangle? I mean, what do you do to calculate it? Yeah, the length times the width. So there are two quantities here. There's the length. I don't really care which one you label which. We tend to label the ones that are widths, the shorter ones. And of course, you also know that whatever the width is, it's the same width on the opposite side. It's true for length as well. It's just that the length on the other side of our river, we're not fencing that part. So the parts that I've drawn in the black lines, that's the fencing part, and then the river is not going to need a fence according to the directions. So far, so good? It tells us one more feature about the area that's important. What does it tell us? Yeah, it actually gives us a value. It's 1,800 square feet. That's really important. We're going to need that. Okay, so the area formula and the area value that I wrote down, that's given information with a little bit of prior knowledge. The imagery was to draw the picture, right? That was like step 1, if you will, from my previous slide. There's also the question that's being asked. What is it asking us to do in this problem? Right, it's talking about perimeter, right? So we need something that shows the relationship between the perimeter of this, and it's not the perimeter of the whole shape, it's the perimeter that's the part with the fencing, right? I don't need the side that's got the river on it. I just need the fencing part. So how would I calculate, or what would be the formula for, more specifically, the perimeter, the fencing part on this particular image?
2L plus 2W.
Okay, so normally it would be 2L plus 2W, but my fencing's not going along my river, so it'll just be L plus 2W. Does that make sense for everybody? All the black pieces are included in that formula. And just like Kaylee just said, we want to maximize, what did I say, minimize, right? We want to minimize this. So I think I've gotten everything written down that we actually have and some equations that show relationships. Good so far? Okay, so if you take a look at some of the guidelines, we've taken a look at 1, we made a visual. On number 2, we identified what was known and what was to be found. And on step 3, we made equations that make this work. But there's a second part of step 3 that we haven't done yet. What have we not done? Yeah, right now both of those equations have 2 variables, length and width, in them, right? But if you'll remember somewhere in algebra, there was this thing called systems of equations where if you have so many equations and so many unknowns, you can solve things. Nod your head if you know what I'm talking about, right? That's where you are at this point. You have 2 equations, and they both have L and W in them. And the first equation, actually, we know it equals 1,800. So as we're taking a look at this first equation, yes, it's an equation for area, but this piece right here, being ever so helpful, means that I can take this equation and I can either solve it for L or for W. We get to pick. And I can use that value to do substitution into the other equation. Okay? So pick. Do you want to do L or do you want to do W? It's sort of irrelevant, but the second equation doesn't have exactly the same components for L and W. Jeffrey, you wanted to make a choice. I can just tell.
Easier, but I can't think of that far ahead. So
Okay.
Just do L.
Just do L. Okay, are you guys good with L? So L would be 1,800 divided by W, right? So down here, I've got 1,800 divided by W plus 2W. And that is equal to my perimeter. So now my perimeter has 1 variable. Are we good? Okay. So as we're taking a look then, number 4 means to determine sort of an upper and a lower bound on what makes sense. Obviously, my length and my width do have confining values. They have to all add up to 1,800. So neither my length or my width can actually be 0, right? Right, I mean, like they can't. And because I did my equation in terms of W, I'll write my limits of what I can have in terms of W. So my W value has to be bigger than 0, certainly. And because there's 2 pieces of W, namely it's the top piece and the bottom piece, the most it could actually be would be, taking a look at this right here, would have to be this has to do with this, right? So my length and my width over here. So I solved in terms of W or L over there, but the W is the same way, right? So these 3 pieces, these pieces have to actually go together. So if you want to say 1,800, that's fine. We're never going to exceed that, but certainly we would have to be somewhere in between these. Okay? So let's take a look then at what happens with the calculus. I'd like to rewrite this for the purposes of calculation in this way. I could use a quotient rule if you really want to, but it works pretty nicely to use a power rule if I just write it as w to the negative 1. So let's take a look and find the derivative of our equation. So what's the derivative of 1,800 w to the negative 1?
Negative 1,800 to the negative 2.
Right. And then the derivative of 2w?
Plus 2.
Mm-hmm. Okay, everybody good so far? Okay. So then, let's see. It might be useful to write this back with the w in the denominator as such. So this is the derivative of the perimeter. I'm going to take this equation and go to my next slide because I'm kind of running out of space. All right, so when we're trying to find a maximum or minimum, and remember this is perimeter, we're trying to find the minimum for, what do we do in order to find a maximum or minimum once we have our derivative? Okay, so what's the next step, though, in the derivative test? You're right. Okay, how do we find which one's the minimum? Like, break it down just a little bit more for me. Do you remember? What do you have, Jared? Yeah, we'll set it equal to 0. That'll be our next concrete step, doing exactly what Jeff wants to do, which is actually finding the solving of that. So we can have this be 2 equals 1800 over w squared, or some version of that. I could multiply the w squared to the other side, right, like cross multiplication.
Would it be -2?
I actually moved this one, and I left the 2 where it was. So yeah, but if I moved to the -2, it'd be okay, because I still have negatives on both sides. Yeah. What would be my next step? Divide by 2, you bet. So now I've got w squared equals 900, and then what? Yeah, we'll square root that. So what will w be? Yeah, so technically it's plus or minus what? 30. Okay, that's technically the answer, but one of those values is not appropriate. Which one? The negative, right? Because we're actually talking about the width of something. So while this is technically the answer that comes out, this is the reason why we sort of talked about what values for w make sense before, is that really they don't make sense to have all values. You know, the 30 is going to have to be the only one that really matters. And even though that's our only option, we still need to verify that it's actually a minimum value. And we can do that in a couple of ways. The first derivative test says that I can take that value and I can make a sign chart. The second derivative test says I could take the second derivative and then evaluate it at 30. And I don't know that either one is necessarily easier or harder than the other one. They're just two ways of doing the same thing. So would you like to do the first derivative test and make a sign chart, or the second derivative test and evaluate? First derivative sign chart. So if I do that, I need the number 30 plotted. And I need values on each side, but they got to be values that like make sense. All right, so like I can't put in 0. Normally I like to put in 0, as y'all know that. But I don't put in 0 because I can't have 0 as a width and it actually makes sense in this problem, right? So I need something else. So again, it doesn't so much matter what we pick. So let me just pick, say, 10 and 40. And we're evaluating it where? In the derivative. And any of the versions of our derivative really are okay. I kind of like this last one that I did that I moved to our other slide, right? The negative 1800 over w squared plus 2. But if you want to use the previous line of that, that's fine too. So we're going to plug 10 into here. And again, what we care about is, do I get a positive or a negative? So if I plug in the number 10, what do I get? A negative. And if I plug in the number 40, what do I get? Okay. Did everybody get those values? Lovely. This is the first derivative test. The first derivative test says what I need to do is to think about this in terms of increasing and decreasing values. So this negative means it's decreasing, and the positive means it's increasing. So what, in fact, is happening here at 30? It's a minimum value. So it's the minimum location. Going back to the problem, of course, I need to make sure that I'm answering what was asked. And so Kaylee told us at the beginning, we're trying to find the minimum perimeter and the dimensions. So I found one of the two dimensions. I need to find the other one, and I need to find the minimum perimeter. So there's 3 pieces of information I really need to find here. W, L, and P. So I found W. How can I find L?
Go back to the area.
I'll put it over here in a second. What was that, Kaylee?
Go back to the area.
Okay, I can go back to the area formula. In particular, you could even go back to the one that's in either in the box or the one right next to it where I solved. The one where I solved is actually fairly nice because, you know, it's in terms of L equals, so that's pretty nice. So if I do that one, then I would have L equals 1800 over 30. So what would L give me? 60. So L is 60. We need to put units on these in a minute, but I'm just writing down values for the moment. And then I need to find P. So how would I find P? Yeah, plug both in where, Jeffrey? In the perimeter equation. So my perimeter equation over here says I have L plus 2W. So L I just found out was 60, plus 2W, which was 30. Whoops, that's terrible, 3. And I get what? 120. And yes, we'll put the units with it here in just a second. 120. Okay, so these are the three numerical values I was looking for. And then I need to answer the question with units that make sense. So my dimensions are 30 feet by 60 feet in either order. And the perimeter is 120 feet. Again, it's feet, right? Not area for feet squared. It's just feet. Let me tell you the most common mistake people make on this question, or questions like this. They forget to verify right here that it's actually minimum. That is the number one mistake that I see people make. They do all the parts here, but they don't actually verify they found a minimum. And I can't remember if it's in, I think it's in the written homework problem. There's one where it feels like it's kind of like tricky because it gives you two values and you actually have to pick which one's the minimum because one's actually not a minimum value at all. So if you just assume they both work, then you're actually making a mistake in doing so. So just be aware that that's a really common place for people to forget to verify. Okay, this is another really common problem. So it says a box with no top is to be built by taking a 6 by 10 sheet of cardboard and cutting X inch squares out of each corner. Folding it along the sides, find the value of X that maximizes the volume of a box. So the best description I can do is think about what would happen if you took like a shoebox and it's in its full form, like it's a box, and you actually slit it so that you made it flat, right? You flattened the box. So you cut it along the corners, right? And you laid it flat. This is the image that you would have. So it would look something like this. You have this box. And there are these pieces that were originally folded up. So my dotted lines are the fold lines. They're not perfectly drawn, but, you know, amuse your imagination, okay? And in your image, for real, you don't really have these corners, right? They don't really exist when you flatten your box. Okay, does that seem okay? When we take a three-dimensional object and we flatten it like that, it's actually called a net. I don't know if you've heard that word before, but that's what we have here. It's an open top box. We don't have a lid. It's just the box on the bottom part. Okay. Now we're going to put in some of the informational pieces that it told us. It told us the original flat box before we cut out the corners and made it into a box is actually 6 foot by 10 foot. So in my image, the way I've drawn it, this length down here is 10, not feet, but inches, is 10 inches. And this length from top to bottom over here, if you will, is 6 inches. And what it's wanting to do is it's actually wanting us to talk about these corners and how big they are, right? How do you form the box? I mean, does it look more like a shoe box that's really like tall for the shoe, or does it look more like, you know, a t-shirt box or a dress shirt box that you buy in the store where it's very flat and it's narrow? You guys know what I'm talking about, right? Like there's different thicknesses of the box. And we're wanting to try to make the box so that we maximize the volume. And that's our question, is how do we get the most possible stuff inside the box? And so it says that these are x-inch corners. So what it's telling you here is that this length right here is x. And if it's x there, it's x on all the corners. So I'm just going to like mark them in red. All of these are the same length x. Okay? Okay, is everybody good so far? All those have length x. That's what we're actually going to find. We want to find that value in order to match. So, it's talking about volume. Do you guys remember how to find the volume of a misshapen box? What, say that really loud, Jared. Length times width times height. That's 3 variables, isn't it? It is. So this is actually all the information that we have. So we've kind of gotten to the end of step 3 where we're supposed to be finding an equation with 1 variable, and we now have an equation with 3 variables. And we don't have another equation like we did in the last problem where we could solve it for 1 and substitute it in. We don't have that either. But we do have some nice imagery over with our box in the picture that I've drawn that's going to allow us to do just that. Okay? Now, you might look at this 10 by 6 and say, okay, well, one of them's 10 and one of them's 6. And there would be if the box remained flat, right? But then the height of your box would be 0, so your volume would be 0, and that's no good. That would definitely not be maximizing the volume of my box, right? So there's got to be something else that I'm doing in terms of volume. And what I need to do is I need to think of that dotted inner rectangle. Okay? That's going to actually be the length and width of the box when it's folded up. So this part in the middle, and I'll highlight it or I'll mark it in blue. This part in the middle is actually the base of the box when it's folded up. So the length and the width are actually referencing the blue rectangle inside because that's the folded box. So what is the length and the width of that rectangle based on knowing that I had the 6 and 10 of the larger rectangle?
It's L minus 2x.
Okay, so in our case, we actually have values. So this would be 10 minus 2x, right? And it's minus 2x because we're subtracting off this little length x here on this corner and this length x in this corner. So there's 2 x's that get subtracted off. And we can do the exact same thing on this one, which is 6 minus 2x. Very good? So over here in my equation, my length and my width now have values. I have 10 minus 2x, and I have 6 minus 2x. What about height? What's my height? It's x. If the box folds up, it now will have a height of whatever that mysterious value x is that I don't know. But as I fold it up, it becomes the height of my box. And fantastic, we have one equation with 1 variable now, which is what we were shooting for. Now, obviously, the length and the width have some restrictions, and x has some restrictions and so forth. Let's actually talk about x, okay? Because x is now my variable in my problem. What are the restrictions on x? What's the minimum that x can't be, so to speak? What can it not be? What's its lower boundary? Can't be 0. If it were 0, I'd have a flat box, no volume, right? So one of the limits on my x here is that my x value has to be bigger than 0. What's the biggest x could be? What do you think? 10. Can't be that big, actually. Can't be that big, but you're getting closer. Can't be 4, but you're getting closer. It's 3.
Oh.
Why would it be 3?
Because you have to cut out on both sides.
You have to cut it out on both sides. So the biggest width that this is right now is 6. And if you cut it out from this side and you cut 3 from both sides, again, you'd have a flat box. So whatever answers I'm getting, if I get anything outside of the 0 to 3 range, they don't actually work for the context of this problem.
So would it be whatever makes that 6 minus 2x 0?
Yes, exactly. And we're using 6 because it's the smaller side. So in theory, if 10 had been the smaller side, we would have the limit to be 5. Yep. All right, let's do just a little bit of algebra, clean this up. So I would have 60, let's see, this is negative 12 and negative 20, so negative 32x. And then plus 4x squared. So I've got, putting in order, 4x cubed minus 32x squared plus 60x. Is that right? You can turn the page. Awesome. Okay, that's what I have down too. All right, so we're at the point where we're ready to do some calculus. Calculus says we're going to take a derivative of this, right? So we're going to take the derivative of volume. The wonderful thing is this is a polynomial. You guys like to do polynomials, so somebody tell me the derivative of this polynomial.
12x squared minus 32.
It's actually minus 64x.
Wait, hold on. What have I done?
Did you distribute your x through to get 32x squared?
Yeah.
Okay. And then what am I missing? Plus the 60. Good. If you'll notice this 12, I'm sorry, I'm getting ahead of myself. And then we're going to set it equal to 0. So if you'll notice, all of these pieces they're even. All right, so they can all at least be divided by 2. I think they can be divided by something bigger than 2. It looks like maybe they can be divided by 4. Does that seem reasonable? If I divide everything by 4, both sides, I would get 3x squared minus 16x plus 15 equals 0. Okay, that looks good. Okay, so good. So far, so good? Okay, spoiler, it doesn't factor. I know. You could try, but I'm just going to spoil it right now. It does not factor. So if you get to a point in a problem where you're looking for some information, and this will happen on the problems that you're working in 3.6 on as well, where it doesn't factor, what that means is that you're going to have to use another method. And this is a quadratic equation. So what method might you use? A quadratic formula might be appropriate, right? Yeah, I know. So we're going to use a quadratic formula. I'm running out of time. Yay for you. That means that we have less to do by Monday, but more to do by Wednesday, so I don't know. 12 one way, half a dozen the other. I don't know, whatever. All right, let's do the quadratic formula really quick. So x equals negative b, so that would be 16, plus or minus the square root of b squared, so 16 squared, minus 4, a is 3, and c is 15, all over 2 times a, which is 3. If we use your calculator, simplify, clean this up, we get two values. They're approximately 4.12 and 1.21. So just real quick, we'll finish this problem next time, but just real quick, are these both values that are going to go on my sign chart? No. One of them's not. Why not? Yeah, it was bigger than 3. We already said we can't be bigger than 3. It doesn't make sense contextually. So we're only going to have 1 point on my sign chart. All right, so clarification. On Monday, you have 3.6 due. I would encourage you to start taking a look at 3.7, either the group work, or not group work, but the homework, WebAssign, or written. But we'll have the written homework and the WebAssign homework due Wednesday instead. We will still finish this lesson on Monday and review for the test on Monday. The test will still be on Wednesday. Okay? See you guys on Monday.